Japan spent billions trying to strip radioactive soil from its land. Standing beneath untouched forests, policymakers realized entire regions would remain poisoned for decades. Then a team stumbled on something astonishing. Ordinary fungi succeeded where advanced cleanup had failed, quietly turning poisoned earth into gardens. If this method works so well, why does the world barely know about it? And who decides what gets left contaminated? The answer begins with the staggering scale of a disaster no machine could contain. Government maps of Fukushima, colored in bands of contamination, defined the future of every hillside and valley after the nuclear accident. The Ministry of the Environment faced an impossible task: how to clean a region where radioactive cesium had drifted across more than 7,800 square kilometers. With billions allocated, officials established a system to prioritize which land would receive immediate attention. They labeled these zones Intensive Contamination Survey Areas, a technical term that decided the fate of entire communities. The criteria were blunt. Areas where radiation levels exceeded 0.23 microsieverts per hour, or where people lived and worked, became the focus. Residential neighborhoods, schoolyards, and farmland were marked for sweeping intervention. Here, excavators scraped away the top 5 centimeters of soil, bagging it in immense black sacks. The waste footprint grew rapidly. By 2019, over 1,285 hectares of land near Okuma and Futaba were stacked with millions of these bags, each one holding contaminated earth stripped from towns and fields. The logic was simple: protect human health first. Cleanup teams measured exposure risk, not just geography. A rice paddy or a playground near a home received urgent treatment, while a forested hillside, no matter how contaminated, was left untouched if few people ventured there. In practice, this meant forests covering 70% of Fukushima's contaminated land remained off limits to standard cleanup. The official rationale centered on efficiency and cost. Removing soil from remote woodlands would require clearing vast tracts, hauling out thousands of tons of earth, and creating even more waste to store. The ministry calculated that the risk of direct human exposure in these forests was too low to justify the expense and environmental disruption. Instead, resources poured into zones where people lived, learned, and farmed. Yet these choices created a patchwork landscape. Cleaned plots stood out against untouched woods, and the waste itself became a new problem. Mountains of bags, some stacked 2 stories high, awaiting final disposal. The process was staggering in scale and price, but it left entire ecosystems and the slow leaching of cesium from forests outside the reach of heavy machinery. Maps and policy memos show the boundaries drawn by these decisions. The ministry's zoning left forests as a kind of shadow land, marked on paper but largely ignored in action. The official focus on immediate human exposure shaped not just the cleanup, but the limits of what conventional methods could achieve. As the machinery moved on, what remained was a silent challenge: vast territories where nature itself would have to find a way to heal. Forests stretch across Fukushima like a living shield, covering nearly 70% of the contaminated landscape. This vast, tangled terrain poses a challenge that no budget or bulldozer can easily solve. Each hillside and ravine holds not just trees, but a deep layer of leaf litter, roots, and undergrowth, an ecosystem that resists the quick fixes used in towns and fields. The numbers alone are daunting. Cleaning just 1 hectare in a forest would mean stripping away hundreds of tons of soil, then hauling it over mountain roads to join the swelling ranks of waste bags already choking storage sites. Multiply that by hundreds of thousands of hectares, and the cost soars into figures that no government can justify, especially when the immediate risk to human health is considered low. Yet the problem does not stay put. Rainfall carries radioactive cesium from the forest canopy down into the soil, and from there into streams and rice paddies below. Over time, these woods become a slow-moving source of contamination, feeding the cycle that cleanup crews are racing to contain elsewhere. The Ministry of the Environment's own estimates show that even if every available worker and machine were put to the task, the logistics of clearing these forests would swallow entire budgets for years, if not decades. Heavy machinery cannot reach most of these slopes without cutting roads that would destroy habitats and trigger landslides. Even then, the act of removing topsoil would leave behind scarred hillsides prone to erosion and ecological collapse. So the forests remain, marked on maps but largely untouched on the ground. The official solution is to do nothing, and it rests on cold calculations: low population density, high cost, and the hope that nature will eventually lock away the cesium deep in the soil or bind it in the trees. But for residents living at the forest's edge, the sense of unfinished business lingers. Every gust of wind, every runoff after a storm is a reminder that the problem is only contained, not solved. The patchwork approach, cleaned fields and schoolyards bordered by untouched woods, creates a visible divide, both on the landscape and in the minds of those who live there. Beneath the surface, the challenge is not just technical or financial, it is a test of imagination. Conventional methods have reached their limits in these shadowed places where the scale and complexity of the forest defy easy answers. Billions have been spent, but the heart of the problem, how to reclaim soil on this scale without destroying what makes a forest, remains unresolved. The opportunity for a new solution hangs in the air, as persistent and elusive as the cesium itself. Shinji Kaneko walked the narrow trails of Fukushima's forests with a question that would not let go. As a professor at Yokohama National University, he was trained to spot patterns others might overlook. The official cleanup had left these woods untouched, yet he noticed something odd among the fallen branches and rotting leaves. In places where decaying wood piled up, clusters of native fungi flourished, sending pale threads, mycelium, through the soil and debris. Kaneko paused, crouched, and sifted the leaf litter. He found that the fungi seemed to thrive even in the most contaminated patches where Geiger counters ticked steadily in the background. Most researchers turned away here, discouraged by the scale and the invisible threat. But Kaneko's curiosity ran deeper. He began collecting samples, not just of soil, but of mushrooms and the tangled mats beneath them. Laboratory analysis revealed something unexpected. The fungal biomass carried concentrations of radioactive cesium drawn up from the surrounding soil. The mycelium, it seemed, was acting as a living filter, absorbing and binding the very element that made these forests off-limits. This observation sparked an idea that challenged everything he had learned about decontamination. If fungi could naturally accumulate cesium, could their growth be harnessed to clean soil without tearing up the forest itself? The simple thought was almost unsettling. Instead of bulldozers and endless waste bags, what if the answer lay in encouraging what was already happening beneath the surface? Kaneko's insight did not come from a moment in the lab, but from repeated walks in these shadowed woods, from watching how life persisted, even in the most unlikely places. He began to imagine a method that worked with the forest rather than against it, a process that used chipped wood as a substrate, inviting native fungi to flourish, then removing the colonized chips to carry away the bound cesium. It was a hypothesis born from observation, humility, and a willingness to trust the quiet work of nature's recyclers. Years later, he would recall those early days as the point where frustration gave way to possibility, and the boundaries of what was thought possible began to blur. Beneath the forest floor, mycelium forms a living web, threading through soil and decaying wood. These fungal networks stretch for kilometers, reaching places machines cannot. Mycelium doesn't tear or churn the earth, it moves quietly, fusing with organic matter, unlocking nutrients, and as scientists discovered, breaking down pollutants that resist even the most advanced technology. The secret lies in enzymes, molecular tools released by fungi. Among the most effective are white rot fungi, native to Japanese forests. Their mycelium produces lacase and peroxidase, enzymes specialized for dismantling lignin, the tough polymer in wood. This same chemistry works on pollutants, hydrocarbons, heavy metals, even radioactive cesium. Fungi release these enzymes into their surroundings, dissolving contaminants and drawing them into their cells. When radiocesium is present, it becomes trapped within the fungal biomass, isolated from soil and water, reducing its threat to the ecosystem. A single gram of forest soil can hold up to 8 kilometers of mycelial threads, each one probing, absorbing, and transforming its environment. Machines scrape surfaces, but mycelium infiltrates every crevice, following root paths and decaying leaves, reaching contaminants buried out of sight. This network accumulates toxins while leaving soil structure intact, preserving the delicate balance of the forest. Native Japanese fungi hold a distinct advantage. Adapted to local conditions, they thrive where introduced species might fail. When wood chips from contaminated trees are spread across the forest, these fungi colonize the chips rapidly. The chips act as bait, drawing mycelium into dense mats that can be harvested and removed, all without deep excavation or chemical additives. This method harnesses processes that have recycled nutrients in forests for millions of years. Enzymatic pathways like lactase and peroxidase are not just selective, they target contaminants while sparing beneficial minerals and leaving the ecosystem's balance undisturbed. Laboratory and field trials show this approach outperforms traditional phytoremediation, offering a gradual but steady path to renewal. The science is intricate, but the principle is clear. Let nature's recyclers work at a scale and precision no machine can match. A forestry worker steps into the undergrowth, boots sinking into damp leaf litter. He carries a chainsaw, not to clear the hillside, but to gather what the forest already offers. Trees felled during routine thinning are chipped on site, their fragments spread in thick mats across the contaminated ground. Within weeks, filaments of native fungi snake through the wood, weaving dense white networks beneath the surface. The process is almost invisible. There is no heavy machinery and no convoys of trucks. The worker returns every few months to check progress, measuring radiation with a handheld dosimeter. At first, the readings barely change, but after 6 months, a pattern emerges. The chips, now shot through with mycelium, show higher concentrations of radioactive cesium than the soil below. Fungi have drawn the contaminant up, trapping it in their tangled threads. By the end of a year, the worker and his team rake up the spent chips, bagging them for safe disposal. Soil samples reveal the numbers. On average, cesium levels have dropped by about 7% in the treated plots. Compared to the slow gains of phytoremediation, this is a leap forward. The forest floor remains intact, its ecosystem undisturbed except for the subtle harvest of fungal biomass. No gullies scar the hillside, and no erosion follows the work. The method is patient, almost humble. It does not promise instant transformation. The numbers are real, 7% less cesium in a single cycle, achieved without tearing up the land or flooding storage yards with new waste. Forestry workers, trained in both silviculture and safety protocols, repeat the cycle: chip, spread, measure, collect. Each round removes a little more of what machines cannot reach. For scientists tracking these trials, the results are proof that nature's slow processes can be harnessed for measurable change. The workflow of chipping, fungal colonization, and chip removal fits into the rhythms of forest management. The evidence is in the data and in the ground itself, where a patch of hillside now registers lower radiation than it did a year before. The question that follows is simple. If this works here, why is it not everywhere? Scaling up fungal remediation in Japan's forests is not a matter of simply spreading wood chips and waiting for nature to do the rest. Each site demands its own validation, because soil composition, moisture, and existing microbial life all influence how well native fungi will colonize and accumulate cesium. Before any chips are laid, researchers must sample the soil and test small plots to confirm that the local fungal strains can thrive and actually reduce contamination. This process, repeated for every new hillside or valley, slows the pace of expansion and requires careful monitoring. Once the right conditions are confirmed, logistics become the next challenge. Forestry crews must coordinate the harvesting and chipping of contaminated wood, often in remote locations with limited access. The chips, once spread, are left for months as mycelium weaves through them, but the eventual retrieval is far from straightforward. Each batch must be collected and transported for safe disposal, adding another layer of complexity. Unlike mass soil removal, this method demands repeated visits and close attention to timing. Remove the chips too early, and the fungi may not have sequestered enough cesium. Wait too long, and the chips may decompose beyond use. At every step, the process must balance environmental sensitivity with practical constraints. The need for site-specific trials and the logistics of chip management reveal why large-scale adoption faces real-world hurdles that go beyond simple policy decisions. Despite the promise shown in field trials, fungal remediation remains largely absent from international soil cleanup protocols. In Japan, most research on mycoremediation has been published in domestic scientific journals, with little outreach to global agencies or policymakers. The United Nations Environment Program, for example, maintains no official guidelines for using fungi in nuclear or heavy metal decontamination. Instead, standard recommendations still favor mechanical removal, chemical treatments, or phytoremediation, even where these methods struggle to reach forested or remote terrain. This gap is not the result of formal rejection or controversy. Rather, The method's low profile reflects a kind of inertia. Decision makers tend to favor established technologies that can be measured, regulated, and scaled according to set standards. Fungal remediation, by contrast, relies on site-specific adaptation and long-term observation, making it harder to slot into existing frameworks. Without champions in regulatory bodies or high-profile international projects, the approach remains a niche solution, tested and proven in limited trials, but rarely considered in the drafting of remediation protocols. The story of Japan's forests is not unique. Across the world, innovative biological solutions often remain on the margins while conventional methods dominate policy and funding. The result is a persistent gap between what is possible in the field and what is recognized in the rulebooks. Until this divide narrows, the quiet work of fungi will continue in the shadows, known to a handful of researchers, but missing from the world's official playbook for healing damaged land. Today, vast stretches of contaminated land worldwide still await solutions as affordable as they are effective. Mycoremediation is no longer just theory. Japan's forests prove what fungi can do. Yet policy and inertia keep these methods on the margins. The challenge now isn't discovery, but adoption. Sometimes revolution grows quietly underground. What would change if we let it surface? Share your thoughts below.